Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 44, Bonding Part 4. Here are our objectives for today's video. Pause here. For the past couple of videos, we've been talking about determining how many bonds and lone pairs there are around central atoms. And the reason why this matters is because we can actually determine what an atom or molecule will look like in 3D space using these ideas. So we're going to be studying molecular geometry, which is just the bond angles and the way something looks in 3D space, and the molecular shape, which accounts for the differences in behavior between bonds and lone pairs. To do so, we're going to be using something called valence shell electron pair repulsion theory, which just means that pairs of electrons want to get as far away from one another as possible, considering that like repels like. And then the number of areas of density, which is the number of bonds, whether they be single, double, triple, or more, that you're not going to see more than that, plus the number of lone pairs. That is what determines the geometry. Pause here. So before we get into the different geometries, it's just really important that you understand what an area of electron density is. So let's break these down. So to determine it, you might need to draw the Lewis dot structure first. So CH4. So to determine the number of areas of density, I look at the central atom. The central atom is carbon. I count the number of bonds, which is 4. So CH4 has 4 areas of density. That makes it a tetrahedral geometry. Now we've got ammonia. So I've got 1, 2, 3 bonds plus 1 lone pair. That is 4 areas of density. So this also has a tetrahedral geometry. You don't need to worry about how I knew that just yet. It's going to have a different shape. It'll be a trigonal pyramidal shape. Now we have carbon dioxide. So I look at my central atom and only my central atom, which is carbon. It has 2 bonding areas. It does not matter that they are double bonding. So this has 2 areas of density. And then sulfur hexafluoride. Right, I look at the central atom, which is sulfur. It has 6 bonds, 0 lone pairs around it. So this has 6 areas of density. It's going to be octahedral. We're going to talk about 2 geometries today, and then we'll talk about the others in the next video. Pause here. So for the first geometry, this will be anytime you've got 2 areas of density. So for example, carbon dioxide. Anytime that you draw something that is linear, it needs to look linear. So the picture here was a hand drawing, so it's not perfect, but you can see that there's approximately 180 degrees between the oxygen atoms. The shape is also going to be linear. We'll talk about shapes a little bit more when we've got more areas of density. Carbon dioxide is an example of something that is linear. Pause here. All right, so carbon dioxide was already in your notes. So for thiocyanate, you're probably going to need to look this one up on your periodic table. It is just SCN minus. So because nitrogen is more electronegative, I'm going to choose to put the extra electron there and label it. And then I start connecting. If you did put it on the sulfur instead, it's not that it would necessarily be wrong. That's another valid Lewis structure, but this is the better choice. But the problem is that that doesn't look 180 degrees. So now that we are in our VSEPR sort of section of it, we are going to need to rewrite it, make it look linear. So now that is complete. So we do need to redraw them from now on. Pause here. So when you have three areas of density, whether that is 3 bonds, 0 lone pairs, or 2 bonds, 1 lone pair, the geometry is trigonal planar. So it's all in the same plane and it looks sort of like a triangle, hence the term trigonal planar. And the bond angles are 120 degrees, which makes sense. They want to get as far away from each other as possible. So on the left, the shape is also trigonal planar. Whenever you don't have any lone pairs, the shape and the geometry are the same. But on the right, the shape is different. It is bent, and that's because of the fact that we've got that lone pair on sulfur. And so if we don't really consider that lone pair when we visualize it, it has a sort of bent shape to it, hence the term bent. Pause here. So for the first one, I've got boron trihydride. And then I could leave it like this because my bond angles look approximately 120 degrees. This has a trigonal planar geometry and a trigonal planar shape. So if I look at this, I look at just the central atom. It has 2 bonding areas because it's 2 double bonds and 1 lone pair. So that means I need to redraw it so that it could look bent. So this has a trigonal planar geometry and a bent shape with bond angles of approximately 120 degrees. Thank you so much for watching and have a great night.